with compound inequalities. So I know you've seen this before, so it's still a lot of review. But there's a way to write a single inequality that describes all the numbers between. So if you want to do, like, I want all the numbers that are bigger than -2 or less than 5, that's the same thing as saying, what are all the numbers, including fractions and decimals, that are between -2 and 5? So we have this thing that, well, we have two inequalities, and we can put them together like this, and that's exactly what it means, is that all the numbers, x, all the values, between -2 and 5. So that's a special way of writing an inequality when you're talking about in between. So we call that just an in-between statement. It just keeps it simple. Of course, when you graph it, you just graph everything between -2 and 5. So between here and here, and everything in between. So any fraction, any decimal between those two numbers. A few details, though. The arrows and the inequality signs, I should say, are always less than or equal to. Okay. What this is saying is basically this. If I covered this up, and it's saying I want -2, it's going to be smaller than my answers. That's why -2 is over here. It's smaller than all my answers. And I want all my answers to be less than 5. When you put those together, where everything bigger than 2, less than 5, is everything in between. So it's really just combining this one, if you flip it around. Okay. Arrow points toward -2. And then what we're going to do, we're going to throw in solving these as well, like adding, subtracting on both sides, or in this case, it's going to be a little bit different. Okay. There is the word and here. It's not going to be too important for right now, but just know that when it's and, it does mean in between. And in between should be linked together. Okay. Okay. So all the numbers that are greater than -3 and they're less than 5. First thing you want to do is realize you're saying, I want all the numbers between -3 and 5. That's what that says if you break it down. So just like that. You notice how the big number is always on the right, the small number is always on the left, and the inequalities are always less than or equal to. They can be also. So all the numbers between -3 and 5. All the numbers greater than 4 and less than 10, that's the same thing. All the numbers between 4 and 10. Oh, wait, by the way, not like that. Yep. The sign does not change. -3 and -3, +5, +5. Yeah, well, that's the only thing that switches. Just imagine the first inequality is being flipped around. It'll never be greater than. Always going to be less than. So this is just the mathematical way of saying in between. -3 is less than our answers, and our answers are less than 5. If you read them piece by piece. Right here it just says -3 is less than our answers. 4 is less than our answer. All our answers are bigger than 4. Okay. So go ahead and do 3. How would you write that? Try that one on your own. See how it goes. It's really just symbol manipulation. Just notice how the pattern of the first two, oh yeah, the first inequality just gets flipped around. The smaller number is always on the left, the bigger number is always on the right. Just look for a pattern. We'll get used to this. So that's how we write in-between statements. Of course, you have to know that -8 is smaller than -1, So negative 8's on the left, negative 1's on the right. So on the bottom one, would negative 5 be an answer? Like if you graphed it, is negative 5 between negative 8 and negative 1? Yeah. Negative 7? Negative 8? No. Why not negative 8? Yeah, it's between. And there's no line underneath, so when you graph these are not solid, these are open. So it doesn't actually include negative 8 and negative 1. They can be solid if they was less than or equal to. So here's the next part. Just watch this first part. Really what this is saying is this. There's two inequalities. Okay. This can be broken up into two inequalities. Negative 4 is less than x plus 3. That's this one. You just drop the less than 7. And then this one over here, you drop the negative 4 less than, and you just have the second part. And you solve each one separately. Subtract 3 on both sides. Okay? That's one way of doing it. Of course, we know from the last slide, this means this, all the numbers between negative 7 and 4. However, there is a little bit easier way of doing it. Anybody see what it is? Yeah. How about over here?
Yeah. There you go.
Just subtract 3 from all three places. That's what's different. And you'll notice you get the same exact thing as we did down here after all that work. So we have a left, a middle, and a right. That's why it's 3 places. We're really solving 2 inequalities simultaneously at the same time. So we're going to try doing the method on the right-hand side as opposed to the left, just because it gives you the same result and it's less work. Of course, can you graph this afterwards? Graph all the numbers between negative 7 and 4. Okay. And when you graph, you don't have to be super specific. Just put put your small number on the left, your big number on the right. You can throw in 0 if you like. Just get the open-close part correct, and then in between, all the numbers in between negative 7 and 4. So 5 is not an answer, negative 10 is not an answer, but negative 6, negative 5, negative 3.5, any fraction decimal between there is a solution. Lots of different answers. Okay. So write this one down and follow along. Let's see, it's pretty fast to solve. So what do you suppose the first step would be?
Subtract 4.
Subtract 4, all sides, or left, center, and right side. Okay, good. Negative 5 minus 4?
Negative 5 minus 9.
I know arithmetic. Divide all sides by 3. There we go. So our answer, all the numbers between negative 3 and 1. Now just notice over here how this is a less than or equal to. So now we have one open and one closed. So on this one, 1 is an answer because of the equal to part. Equal to is always a dot.
Do the sign still change when you divide by negative?
The signs will still change if you divide by a negative, yes. Both of them. So if this was a negative 3, then yeah, we'd switch both of them and then flip the whole thing around, which I'll show you. Of course, when you graph it, open, close. The equal to. Equal to means a dot. Means 1 is an answer. Of course, everything in between. Not too bad, right? Okay. Now, as someone pointed out before, how would we start here? Good. Negative 4 minus 6. What goes in the middle? Negative x. Because it's 6 minus x, so just the 6 gets there. Divide by a minus 1. Yeah. So now you can see if you divide by a negative, yep, switch both signs. Now you can see it's messed up now. The big numbers on the left, the small numbers on the right, and they're facing the wrong direction. They're all greater than. So flip the whole thing around. So flip it around to be the correct format. Negative 2, less than 10, less than or equal to 10, actually. So that's all the numbers between negative 2 and 10. So small number, no matter what, always on the left. Bigger number, always on the right. All the numbers between. And that can be graphed. One open, one closed, and everything in between. Not too bad, right? Go ahead and start on the front. We'll talk about the back in 10 minutes or so.
Oh, that's gonna ruin the paper. It's not even evenly.
So to start this, I'm just going to write the work below since the number line's in the way, but same idea. So it's x plus 3, subtract 3 from all parts. Left side, middle, right side. Positive 3, negative 3 is 0. Bring down the inequality signs, less than or equal to on the left, less than or equal to on the right. Remember, these can be different though. You have 1 and 1, or they can be the same. There's only 2 possibilities though, either less than or less than or equal to. 1 minus 3 is,
21.
and 5 minus 3 is positive 2. Yeah, that's it.
These cargoes, he's different. Two guitars. No, finish with it.
Alright. Now graph it. All the values between negative 2 and 2. Just like that.
Is that Shante?
Here we go. Let's do 3.
Right.
So what should we do on 3? Divide by 9. So 0 divided by 9? 0. 9 divided by 9 is just 1. Nine divided by 9 is 1. Just pay attention to the inequality signs. We have one that's closed, one that's open. So we have
Take my phone.
DeAndre. And then connect them. So you can just go like this, or you can make this bridge in between. Either way, it makes. If you choose to make the line for your answer on the line as the number line, just make it thicker so it's obvious. If you draw just a, right on top of it, it's not easy to read. All right, any more on this left column on the front side? 5, 7, or 9? 7. Be careful with your values, right? That's all. Subtract. Sand everywhere. What's different about this? Divide by. So we have positive 3, and then we switch the signs. That's what's different with the dividing by a negative everywhere. We have B. Switch the sign, yeah. And then flip everything around. So this is going to be everything between 3 and negative 9, which is the same as everything between negative 9 and 3. Now you have to rewrite it this way. So the arrows are facing to the left. Flip the whole thing around, like you're holding a mirror up to it. You saw a reflection. So you see how the arrow faces the negative 9, and so does it here. And it's open to 3 here, and it is here as well. Okay? And then we can go ahead and graph it. And you'll have a clue of the numbers you get. If it doesn't land on the graph, you know something's up. So we have this open or closed, right? Open. Open. And connect. All the numbers between negative 9 and 3. All right, go in and work with by yourself or work with someone. Finish up the front. Check with each other. and then graph it. I suggest check the answer and then graph, and once you know, well, okay, I checked with a few people and they all got the same answer. Okay. All right.
Hey, John Clark.
Thank you. All right. Take a look at the back. Let me just show you a few examples, but then we'll go straight to working, finishing it up. So this, listen up, Chris. Right? So this is like the opposite. When they have the word or in them, instead of being between here and here, it can be to the left or the right. So the graphs will actually look like the opposite. So the opposite of everything in between would be everything that's to the left and everything that's to the right. So when you see the word or, you already know what the graphs will look like, going opposite directions, this way or this way. But as far as solving it, you just solve each individual. You notice there's no in-between or statement. They just give you two inequalities. So you just solve them individually, just like they're two different problems, but you graph them together. One could be open, one could be closed. The same rules apply for that. But it's nothing more than that. So the back is actually a little bit easy. You don't have this new format or anything. The one thing I will go over is the last four. The last four problems are all the special cases, the no solutions, the infinite solutions, and what does that look like?
Isn't there way going both ways?
Well, yeah.
I'm starting.
So here's some special cases. Not these, sorry. Looking for these right here. What numbers are bigger than 5 and they're less than 3? What numbers are bigger than 5, greater than 5, and they're also less than 3? 4.
I'm just playing.
Yeah, it has to be both. So you can see this is a good example of a no solution. How can a number both at the same time be bigger than 5 and less than 3? Likewise, what numbers are bigger than 5 or less than 3? So there's a few weird cases where the things overlap are quite different. That's what the last four will be. You'll see some all reals. You'll see some no solutions. What numbers are greater than, like on number line, if I did this, this is like 4, 5, and 6. What numbers are bigger than 4 or they're less than 6? Okay. Bigger than 4 or less than 6? Well, every single number is bigger than 4 or less than 6. That'd be like all real numbers because every number works. So there are some of these special cases when you get everything or you get nothing. It really has to do with the word and the word or. Or is less restrictive, it can include more points, and is everything has to be true, both of them. Okay. So on the back, so we have negative 3x greater than or equal to 9.
That's positive 9.
Make sure you switch the sign. So all the numbers less than -3 with an equal to, actually they both have equal to. So that's everything going this direction, less than. And then everything greater than -1. Opposite direction. And the oars generally do go in opposite direction. I don't know.
I'm sure.
Let's go to -17. Divide everything by -9. Of course, divided by a negative, switch the signs. R. -7 on the left. -6 on the right, is that correct? Now, flip it all around. Now, what is different or weird about this compared to the other ones we did in the front? Something off. Well, two things had to be true for the in-between. Number one, they had to be less than or less than equal signs only. And the second thing was the smaller number had to be on the left. But here, when we flipped it around, it puts the bigger number on the left instead of the smaller number. So it's kind of like, well, there's no way to write it in the correct format. So this is one of those exceptions where you get the no solution, not able to graph this. Doesn't follow the rules. That's 17. Okay, finish up the back. Walking around, collect to see what you have done.